Hello everybody, I will start my today's another live coding session. So in my today's video, I will solve this question, word rudder. So in this question, a transformation sequence from word, begin word to word, end word, using a dictionary word list is a sequence of words, begin word to S1 to S2 to blah 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 to SK, such that every adjacent pair of words differs by a single letter. Okay. Every SI from 1 to K is in word list. Okay. Note that begin word doesn't need to be in the word list. I see. And SK is equal to end word. Okay, so I have the begin word and the end word, which is the target word. And the begin word doesn't necessarily exist in the word bank. Or let's just say word list. Yeah. However, from the next word of begin word until the end word, all of them should be in the word list. Okay. And for each transformation, I will choose exactly one character and then swap it with adjacent character. In the case of C, it should be swapped with B or D. And in the case of A, it can be swapped only with B, I guess. Okay. So given two words, begin word and end word, a dictionary word list returns the number of words in the shortest transformation sequence from begin word to end word, or 0 if no such sequence exists. Okay, so I will be given the string word list, no, string begin word and string end word and list of string, which is word list, and I will return the integer. So for example, in this case, there was, including begin word and end word, there are 5 strings in the sequence, so I return 5. Okay. Good. So that being said, let me write some example. Okay, so in this case, in this example, I start from hit, and this hit doesn't exist in the word list. Yeah, and from here, I move to the say hot. This is possible. No, not possible. Wait. Every adjacent pair of words differ by a single character. Every adjacent pair of words differ by a single. No, this is possible. So I can choose. Sorry, I was saying something wrong. Yep. So when I have a word hit, I can choose any character, single character like I. Then I can swap it with any character. HAT, okay. HST, okay. HZT, okay. Yeah. So HOT is possible. Then say I can swap it to LOD, H to L. Then I can swap it to log, and then I can swap to cog. So yeah, actually this is the answer which is given in the example. Yeah. So I will obviously have to confirm if there isn't any sequence which is shorter than this. And once I can confirm it, I will return 5. So this is it. Okay. So now I have a clear image on this question. So I will think of the algorithm I can use. So obviously, I think the brute force approach for this question is that I will do the kind of um, every possible, sequence. I will try. So, say when I have the hot, I try to go to hot and then dot, or I can go to lot is possible. Yeah. So from dot, I'm pretty sure I should never come back to the previous word because it's just a waste of the ranks. So for getting hot and dot, I can move to dog or yeah, lot. Yeah. So in this way, um, for I will choose every possible next word, and then I go that word. I will continue that. This is kind of the DFS approach, I can say. So I will use the DFS to check every possible path from begin word to end word. Then, um, yeah, I will return the shortest length of every possible path. So that's the brute force approach. And it's not easy to estimate how much time this will take, but the upper bound, loose upper bound is, I can say, n times n minus 1 times n minus 2 minus n minus 3. Yeah, blah, 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 1. Yeah, because every time I choose a word, I have every other choice which can come next. Theoretically, maybe this isn't true, but when I think of the upper bound, yeah, I can think it in that way. So that's the brute force approach. Okay, and now I will think how we're going to optimize this. So I'm pretty sure because I'm looking for the shortest path, I can use the breadth first search. Yeah. So theoretically, in the worst case, both of the DFS and BFS takes overwhelming time. Yeah. But oh, wait a minute. So no, it takes more than that. Sorry, not overwhelm. So I mean, even if I use the BFS, just think that the ranks of the path, shortest ranks of the path is exactly n, length of the word rest, plus 1. In yeah, oh sorry. Let's assume it is n. In that case, even if I use the BFS, I will check n, yeah, n possibilities first. Then from each, I will take a look at n minus 1 possibilities in that way. Yeah. Okay, so that being said, I can think of this as a graph question. So one thing I can do is I will think of each path I can think of, say from heat to maybe hot, dot and rot. So there is an edge, hot to dot, hot to rot. And also there are edges, dot to dog, dot to rot, and rot to dot, something like that. Yeah. So and from that, I can do a kind of BFS or DFS. Yeah. Oh, but also I can say I'm looking for the shortest path. Yeah, so maybe. So, I mean, if I use the BFS, I don't have, yeah, obviously I don't have to think of the same string twice because, say, if I can reach ABC, so I will show example. Say if I have AAA and I can go to AAA or ACA or something like ABA, then let's say I can go to A. Yeah, obviously from ABA, I can go to ACA, but I don't have to think of this ACA because ACA is already visited in a single, transformation. I mean, single move. So once I see the word, I can mark each word as the seen, or I should say visited. So in that way, the time complexity should be O of n plus e. N is the number of words, which means that's the number of nodes in the graph. And e, let assumes that this is the number of edges. So number of combinations where words can move, yeah, from one word to the other. So with assuming those, the time complexity should be O of n plus e. Okay, good. So I think this is an approach I can implement. Yeah. Oh, sorry, but even with the DFS, I could use it. I could just mark the word which is already visited. Oh no, it doesn't work. Yeah. Oh no, it does work. So if I so say if I visit dot from hot, then I don't have to visit hot anymore. I actually didn't write it. And it suggests that this is already visited, marked as visited. Hmm. Okay, so that's the approach I can take. Yeah. Wait, no. Sorry, in the DFS, it's not possible because I will go until the end of the word and go backward and visit the next node. So if I backtracks one word or two or three words, then if I choose another way, I completely forget which path I went in another, ramification. So I cannot, you know, trim the path to be visited. Okay, so that being said, I will use the BFS. So I will outline my thought. So firstly, I will build the agency list and then I do BFS. And I will return the shortest path. Or 0. Okay, this is it. Okay, so let me start the presentation. So I will build the adjacency rest in here. Then I will implement this later. And then I will do the BFS from begin word. So if begin word is equal to the end word, oh, in that's the case, I can safely put it in the queue. Okay. And also I have to return the length of the path. What do you mean? Queue should be deck. I will pop up the previous node, and then I will visit every possible, adjacent next word from here. And if already visited, I skip it, but otherwise I visit it. So if the current word is exactly the end word, I will return. Otherwise, this means that I can just visit the next current word, and I will count. Yeah, so in that case, I push it into the queue. Okay. And also I marked it as visited. Okay, so that being said, if I reach line 52, which means that I, couldn't find the word, even though I visited all the possible words which can be reached from the begin word. In that case, I will return 0. Okay, so this is it. Oh, yeah. And in this question, oh, I forgot to tell something which is important, maybe important. So all the words, ranks of all the words in the word list and also the begin word are the same. And the ranks is from 1 to 10. So this means that I can assume that this is almost a constant space. Yeah. So, and also checking the adjacent word here in line 44 takes a constant time. Yeah, because they're up to 10 characters. But if I will also take care of that, the time compression should be ln L times n plus e. So which should be ln plus le. Oh, but I forget to tell the time compressed for building the adjacency arrays. So I will talk about it after implementing the build adjacency arrays. So let me think how we're going to implement this. So the quite naive approach is that, say, I have AAA and AAB and ACC and AAA again, or something like this. Oh, by the way, all the words in the word list are unique. Okay, good. Yep. Wait, so in this adjacency list, I can move from anywhere from begin word, but from word list, any word in the word list, I cannot move to the begin word. So I have to take care of it, maybe. Or maybe no, because even if I go back to the word begin word from the word list, word in the word list, it's not the shortest path, so I don't have to take care of it, maybe. Yeah. Anyway, let's assume I have these strings. The naive approach is that from AAA, I will check each word if AAB is the adjacent, and if it's true, I register AAA to AAB and also AAB to AAA. Yeah. So in that way, it will take all of this n squared time to build this adjacency list. And each comparison, two words comparison takes O of L, so it should be L times n squared. But actually, I have a better way to do this a bit more, optimized way. I will introduce that. So for I will use the you know regex. So character which can be moved from this AAA is something from BB, sorry, something AA or A something A or AA something. So what I can do is I will, have the hash map which maps from the regex to every possible word in the word list. So for example, in this case, there is only AAA. Say A sharp A. There are, let's say I have ABA. AAA and ABA. Yep. So in this case, this should be this. So when I take a look at ABA, so for A sharp A, I can append it here. So when I append this is the timings that I find this, adjacency, edge in the graph. So when I append this, I can say AAA and ABA are adjacent. Yeah. And for example, if I have ACA, when I add ACA, I will take a look at every possible, strings in this list, and I create the, edge between AAA to ACA and ABA to ACA. Yeah. So that's how it works. So in this approach, I guess time complexity is a little bit, compact. Optimized. Mm. Wait. So wait, do I really have to build the adjacency list from here? Maybe just this regex to the word list is enough, or I should say word set should be enough. So say if I have AAA, ABA, ACA set from H asterisk A, say if I have ACA in the BFS, this can be mapped to A sharp A, sorry, sharp CA or AC sharp. So this means that I will take a look at each, you know, regex to word list mapping, and I will check each word. Also, I can do. Oh no, yeah, that's it. So in that way, I think I can find the adjacency words from each specific word. Yep. So yeah. So I will not build the adjacency list, but instead I will create something, some data structure like this. So I can call it like, yeah, regex to word hashmap. So with using this in BFS, I can speed up. So this will take overwhelm time to build the adjacency list. No, regex to word list. And with using that in BFS, actually the time complexity doesn't change in the BFS because all I have to do is from I say if I have the word ABA, I will think of the word sharp AA, A sharp A, AA sharp. And I will take a look at each word in the word set values. So theoretically, this just checks every adjacent word which is built in the adjacency list. Yep. So the time complexity doesn't change in BFS part. So in that way, I could optimize, the typing complexity. So let me swap the implementation with this. So in here, in line 45, okay, so let me, yeah. I will take a look at each regex. Then in this way, I guess the current word. Hmm. Good. Okay, so that being said, I also have to implement two regex method. Yeah, but that being said, I will start from build regex word method. So as I said, now I don't take care of the begin word or word in the word list. Yeah, for the implementation simplicity, even if the word in the word list to begin word arrow is made, it will not be used because it just comes back to the begin word And because begin word is marked as the visited in line 36 before the BFS, so that kind of edges doesn't help. Yeah. Okay. So does that being said, let me quickly change the implementation here. So I will create the set of the words. And I will pass that words to the build regex to word method. In this way, the implementation becomes a much bit simpler. Yeah, like this. Okay, so my final task is to implement the toRegex method. Sorry, so this should be toRegexes. So I need to do it like this. Okay. So let's say then I build the word. So and I return them. Okay, so this is it. So let me take a look how it works with very simple example. Yeah, like this. Okay. So in this case, the word path I'm looking for is hit to hot to cat, obviously. I will take a look. In line 39, I initiate the list of the words with hit hot cat. And I create the regex to word, hashmap. Here, I assume that build regex to word method is correct because I try to focus on the main method. If there's a problem when I execute the code, I will take a look at regex to word method. So let's assume that now regex to word hashmap looks like this correctly. And also I have hot. Hot should come here. And also HA something to hot. Then I have cat. Yeah. So this is a regex word that will be created. And then in line 55, I initiated Q with only with the begin word, which is hit. And okay, I start with these. So the first thing which happens is that I will check in line 63 if I have something in the queue. Yes, and current ranks becomes 2. And previous is now q.pop left is now hit. So in line 67, adjacency priv, adjacency hit should wait, what I'm doing here. I don't need this line. So in line 67, I will convert this current to regex. So current word hit is converted into 35 to 37 keys. And for each, I will take a look as the current word. So for example, hit is already visited, so I skip it. Yeah. And in line 71, I will check if any of them is equal to the word cat. Not yet. In that case, in line 73, I will append the current word to Q and also add it to the visited set. So I can simply skip hit. So only the word I have to take here is hot. So when current is equal to hot is not visited and hot is not equal to end word. So I append this hot to the queue. Then I added this to visited. Good. And now I come back to rhyme 63. And now rank Q is not 0, it has hot. And now current ranks becomes 3. Okay. Then in line 66, hot is now prev. And in this should be prev. Yeah. So for the regex of the cat is something at c something t, and c a something. So I will take a look at this and this and this. But because cat is already visited and also cat is already wait. So sorry. Now pre-word is now wait. Oh, my mistake. So actually, if the search word is hit and end word is cat, I can visit it in one path. I mean, one move. Which means that when current is equal to cat, I could finish it. No. Wait. I'm a bit confused. So hit. Then I popped out hot. Sorry, it's okay. So when I have hot, So now regex should be h something t and something at h is something. Yeah. So these are the current words. And first for sharp at, because hot is already visited, I have cat here. So here, yes, I find cat. So I return the current rank 3. That's the end. Okay, it works. So I could cover lines 56 to 74. And I'm pretty sure that if I can't find the word, I return 0 in line 75. So I'm pretty confident about my code, especially the main method that I execute. This should be odd. This is typo. Okay, since this is not correct, let me quickly check to regex this method first. Wait, word is overwritten here. Let me name it regex. Good. Now I submit my code. Accepted. Great. Okay. I will quickly talk about the space complexity. So for space, I need this regex to word map, and also in the BFS, I need Q and visitor set. Yeah. And for regex to word, number of keys can be up to, Rn. Yeah, Rn. In the case where any regex never duplicate. And also for values, there should be Rn values in total. Yeah, because each word is mapped from R regexes. And now I come back to the main method and Q. This could be up to Rn. In the case when, for example, I have a one word, start word, then every word existing in the word list can be reached from the current, start word. In that case, all the words in the word list should be pushed into the queue. So their n element is a queue. And each element is ranks L. That should be Ln. Okay, and now the next thing I have to take care is the business set. Yeah. Obviously, this is Ln. Yeah. When all the words are, or I should say, almost all the words are included in the business set. Okay. And I will assume that L is almost ignorable because it's up to 10 characters. Yep. So the good thing about this approach is that I didn't use the adjacency list, so it doesn't take time or when squared. Okay, so that being said, let me quickly wrap up my today's coding session. So in this video, I solved the question word rather. And this is a question where, in which I will be given two words, begin word and end word. And my task is to find the path, shortest path from begin word to the end word, going through the word in the given word list. And for this question, I could take it as the graph question. and I could think that each, adjacent word. Okay, sorry. I mean, each word represents a node, and for adjacent words, there is an edge between the corresponding nodes. So that's how I can see the program as a graph. Yep. And that being said, I had to do the BFS from begin word to the end word. And one optimization I made was that I didn't use the adjacency rest because building the adjacency rest could take all of n squared, assuming that there are n words in the word rest. So I didn't do that. Instead, I created the map like the regex to the word hashmap. And by using that, say if I have AAA, I will if I'm at the node AAA, the regex should be sharp AA or A sharp A or AA sharp. So the next word, which can be reachable from AAA, is a word which is represented as those regex, like BAA, CAA, or AZA, AAX. Yeah. So in that way, I can find the next word from the current word. Yeah. So in this way, actually, the time compressor doesn't take n squared time. It can be done in O of n. Yeah. In BFS. So this is a good point about this optimization. Okay, that being said, I finished my today's coding session. Thank you so much. Bye.